Hi, this video is about ray tracing. Ray tracing is a fundamental algorithm to render 3D scenes in a realistic way. It is the basis of many photorealistic rendering methods that are used extensively in movie production rendering. In rendering, first the surface visible through a pixel should be determined by computing the first intersection of the surfaces and the half line starting at the eye position and going in the direction of the given pixel. In local illumination rendering, having identified the surface visible in a pixel, we have to compute the reflected radiance due to the direct illumination of the light sources. We prefer abstract light sources for the sake of simplicity, since an abstract light source may illuminate a point just from a single direction. The intensity provided by the light source at a point is multiplied by the BRDF and the geometry term, which is just the cosine of the angle between the surface normal and the illumination direction. The intensity provided by the light source is zero if the light source is not visible because of some other object which is occluding the light source from the shaded point. The visibility of light sources from a shaded point can be determined by sending a ray from here into the direction of the light source and checking whether or not this ray intersects any object before reaching the light source. For directional sources, the intensity and the direction are the same everywhere. For point sources, the direction is from the source to the shaded point and the intensity decreases with the square of the distance. The BRDF times the geometry factor equals to the following expression for diffuse and foam blind type materials. Here we use different product symbols for different data types. The asterisk is for spectra, the small dot for multiplying spectrum with a scalar, and the big dot is the dot product of two vectors. The plus sign in the superscript, like here, indicates that negative dot products are replaced by zero, since this corresponds to the situation when the considered object occludes the given point from the light source. In the local illumination model, all surfaces that are not directly visible from the light sources are completely black. However, this is against our everyday experience when some light indirectly illuminates even the hidden regions as well. So we add a so-called ambient term to the reflected radiance, which is here, where the intensity LA is uniform everywhere and in all directions, and the ambient reflectivity Ka is a material property. If we want to be physically plausible, Ka can be obtained as the diffuse coefficient multiplied by pi. Note, however, that the modified model with the extension with this ambient term is still very far from a physically plausible simulation, which is called global illumination. A fundamental operation of ray tracing is the identification of the surface point that is hit by a ray. A ray is defined by its start and direction. When transparent objects are also considered, it is useful to store whether the ray is inside the object or not, so whether we have to use the index of refraction of the material or its reciprocal when the ray arrives at the surface from the inner part. The ray may be a primary ray originating at the eye and passing through the pixel, or can be a shadow ray originating at a shaded point and going towards the light source, or even a secondary ray that also originates in the shaded point but goes into either the reflection or the refraction direction. The intersection with this ray is on the ray, thus it satisfies the ray equation, which is here. It says that for some ray parameter t, the points on the ray satisfy this equation. We restrict the domain of the ray parameters to positive values. By emphasizing the constraint of positive ray parameters, we have a half line or restrict the visible objects to those that are in front of the eye. A ray may intersect more than one surface, as you can see here, when we need to obtain the intersection with minimal but positive ray parameter, since that's the surface which occludes other potentially visible surface points. Function first intersect finds this point by trying to intersect every single surface and always keeping the minimum and positive ray parameter t. The implementation assumes the existence of an intersect function for every object type, which returns a hit structure if there is an intersection. This hit structure contains the ray parameter t, or a negative value just to indicate that there is no intersection. In addition to the ray parameter, this structure also stores the position in world coordinates, the normal vector of the surface at the hit point, and also the material properties here. So intersection calculation should also determine the normal vector of the surface at this particular point. Recall that when we established formulae and implemented the functions for reflection or refraction direction computation, we assumed that the surface normal points towards the incoming ray. So the dot product of the ray direction and the surface normal is negative. To make sure that it always happens, it is worth checking whether this is the case, and if it is not the case, we can flip the normal vector into the other direction. The implementation of function intersect depends on the actual type of the surface, since it means that the inclusion of the ray equation into the particular equation of the surface. The first example is the sphere. Substituting the ray equation, which is here, into the equation of the sphere and taking advantage of the distributivity of the scalar product, we can establish a second-order equation for unknown ray parameter t. A second-order equation may have 0, 1, or 2 real roots. We have to emphasize that complex roots have no physical meaning here. So the real roots correspond to the cases when we have no intersection, we have just one intersection since the ray is a tangent to the sphere, and when there are two intersections, when the ray enters the sphere and then later exits it. Recall that we also need the surface normal at the intersection point. For a sphere, the normal is parallel to the vector pointing from the center to the surface point. And it can be normalized rather easily because we know the length of this vector, so dividing by r, the radius of the sphere, we obtain a unit vector. I have to emphasize that this simple normal vector calculation is valid only for the sphere. On the implementation level, the abstract definition of an object that can be rendered with ray tracing is provided by the intersectable class or structure, which has material properties and an abstract function, a pure virtual function called intersect. The intersect function can be given a real body if we know the equation of the surface. Therefore, specific types, like for example the sphere, can be inherited from the general abstract type called intersectable. Here, for example, for the case of the sphere, we know that a sphere can be defined by a center and the radius, and the intersect calculation can be implemented as the solution of a second-order equation. The equation of the sphere is an example of a more general category of implicit surfaces that are defined by an implicit equation of the x, y, z Cartesian coordinates or the position vectors of surface points. Substituting the ray equation into this implicit equation, single variate equation can be obtained, which is typically nonlinear. So we may have different algorithms, at least numerical algorithms, to find the solution. So let us denote smallest positive root of this equation by t star. Substituting t star back to the ray equation, we can obtain the Cartesian coordinates of the intersection point. Recall that we also have to find the normal vector at this point. In case of implicit surfaces, the normal vector can be obtained with the gradient calculation, which means that we have to obtain the partial derivatives with respect to the three Cartesian coordinates, and these three derivatives form the three components of the normal vector. To prove it, let us express the implicit equation around the intersection point x star, y star, z star using Taylor's approximation. After Taylor's approximation, we can say that this term is 0 because the intersection point is on the surface. And we are left with this expression, which is equivalent to the equation of a plane where x, y, z are the Cartesian coordinates of the running point. X star, y star, z star is the position vector of the plane, and the three partial derivatives are the components of the normal vector. The triangle is one of the most important primitives because we often use it to approximate arbitrary surfaces. So effective ray triangle intersection algorithms are still in the focus of research. Now we present a very simple solution for ray triangle intersection. This simple algorithm consists of two steps. First, the intersection between the ray and the plane of the triangle, and then in the second step we determine whether the intersection point is inside the triangle. Suppose that the triangle is given by three vertices R1, R2 and R3. The equation of the plane is usually given in this form. So we have to find the position vector of the plane and the normal vector of the plane. The position vector of this plane can be any of the three vertices, and the normal vector can be obtained as the cross product of the two edge vectors, like here. So, having established the equation of the plane, we can substitute the ray equation into the equation of the plane, which is going to be a linear equation for unknown ray parameter t that can be solved, and we will obtain this solution. If parameter t is negative, then there is no intersection between the half line of the ray and the plane. If t is positive, then this t can be substituted back into the ray equation, so we can obtain a point P on the plane. Now we should determine whether this point P is inside the triangle. An edge separates the plane into two half planes. A good one, which is on the left in this particular example, that contains the triangle and also the third vertex of that triangle. And a bad one, which is empty. Point P must be on the good side, where the third vertex is also located. Points on the left or on the right with respect to edge R1 to R2 can be separated using the properties of the cross product. Assuming that we look at the plane from above, this cross product R2 minus R1 cross P minus R1 will point towards us if P is on the left-hand side of this edge. As n, the normal vector, also points towards us, we can check whether the two vectors have the same direction by computing their dot product and checking if the result is positive. Because the dot product of two vectors pointing into the same direction is always positive, but the dot product of two vectors that are pointing into two opposite directions is always negative. So a single inequality can decide whether P is on the good side with respect to the edge or on the bad side. If it's on the bad side, so this inequality is not met, we can terminate further calculations and say that P is not inside of the triangle. However, if all three edges indicate that P is on the good sides of these edges, then P must be inside. On the top level, ray tracing rendering visits pixels one by one. Every pixel, the virtual camera has a point on the window rectangle which corresponds to the screen in the virtual world. The origin of the primary rays is always the eye position. The direction of the ray is from the eye towards the point on the window rectangle, which is calculated by a getRay function. With this ray, function trace is called, which computes the radiance transferred back by this ray, having identified first that point which is first hit by the ray, then obtaining the radiance reflected in this direction. The radiance on the wavelengths of red, green and blue is written into the pixel, and if we process all pixels, our final rendered image will be available. To implement this getRay function, the virtual camera should be defined in the virtual space. The user's location is specified by the position vector called the eye. The display surface is represented by a 2D rectangle in the virtual world coordinates. The center of this rectangle is specified by a point called lookat, and its orientation and size are defined by two additional vectors called right and up. Any point on the window can be obtained by first going to the lookat point and then using a combination of the right and up vectors. The combination parameters alpha and beta are between -1 and 1, so they are in fact normalized device coordinates. If the resolutions xm and ym of the physical screen are known, then x and y pixel coordinates can be easily converted to normalized device coordinates that can be used as combination parameters of the two vectors. So we obtain P. The direction vector of the ray is just the difference of P and the eye position. The trace function gets the ray that involves the origin and the direction vectors. First, we compute the intersection that is in front of the eye and is closest to the eye. This is done by the already implemented first intersect function. This function indicates with a negative ray parameter in the returned hit structure if there was no intersection. If this is the case, the trace returns with the ambient light, since if we cannot see anything, we see the ambient light. If some surface is seen, trace computes the contribution of the abstract light sources. To check the visibility of a particular light source, another ray called the shadow ray is traced from the shaded point into the direction of the light source. If this ray intersects an object and this intersection is closer than the light source itself, then this light source is unable to illuminate the point, so the point is in shadow. If this is not the case, the contribution of the light source using the diffuse plus Spongbrin formula is added to the output radiance. This for loop considers all abstract light sources one by one. Note that the start of the shadow ray is pushed a little into the direction of the surface normal n in order to avoid situations when numerical inaccuracies result in intersection with the identified surface with not 0 but some positive ray parameter. This would produce ugly black dots on the surface as shown by the figure. For future implementations, let us call this part of the program as direct light calculation, because these few lines determine the contribution of direct light source. To simulate also smooth, optically perfect surfaces responsible for mirroring or light refraction, the local illumination model should be extended. When the surface visible from the eye is identified, we calculate the radiance as the contribution from abstract light sources in case of rough surfaces, as we did it before. However, for optically smooth surfaces, the reflection of the radiance from the ideal reflection direction is computed, and for transparent objects, also the refraction of the radiance coming from the ideal refraction direction is computed. According to physics, the scaling factors are the Fresnel function or 1 minus Fresnel function respectively. This equation expresses the radiance of a surface point in a given direction as the function of the direct light sources and the radiance coming from the ideal reflection and refraction directions. The question is how these new terms can be obtained. Let us recognize that the computation of the radiance delivered back by an ideal reflection ray or a refraction ray is exactly the same problem what we are solving right now. Just the starting point of the ray and the direction of the ray should be modified. So we traced back the solution of a problem to the solution of the same problem, which means a recursive implementation. So in this generalized trace function, the trace gets the ray as before. First we calculate the first intersection if it exists. If it doesn't exist, then the function returns with the ambient light. If this surface is a rough surface, the previously implemented direct light function is used to compute the output radiance. If the surface is smooth, then the reflection direction is calculated, and the same trace function on which we are working right now is called recursively, and when it returns the radiance coming from this direction at the shaded point, that radiance is multiplied by the Fresnel factor. And the same happens with refractive objects. The only difference is that instead of reflection direction, the refraction direction is calculated. Note that there are cases when there is no refraction direction, so it should be checked. And obviously when there is no refraction direction, there is no additional recursive trace cause. Recursion is a very dangerous operation if we cannot make sure that it terminates. Assume, for example, that this is a glass ellipsoid object. The ray can get refracted into this object and then it can get reflected infinite number of times on the inner surface. So our program will surely crash with a stack overflow error. We should limit the recursion depth for any price. This is possible by introducing a new parameter indicating the depth of recursion, and we call it d. So when the depth of recursion is greater than a predefined limit called max depth, we terminate further calculations and return with the ambient light. And at each recursive call, this depth parameter is incremented. Ray tracing is a very elegant algorithm. The implementation fits just a business card as it is shown here. This is the business card of Paul Hagbert. But despite to its simplicity, it can render shadows, ideal, reflecting or refracting surfaces in addition to rough surfaces. Object-oriented decomposition identifies objects representing the problem. These objects are defined in an abstract way by specifying what operations can be executed on these elements. So using this approach, we can also specify ray tracing algorithms in an object-oriented way. The virtual world is represented by the scene class. A scene can be built, can be rendered, which in turn requires the ability to trace a ray, which in turn needs to find a visible object with the first intersect method. Ambient light is a data member of the scene. The scene has embedded objects like the camera and light sources. The camera serves the rendering algorithm with its getRay function. The scene is also a collection of intersectable objects. Intersectable is just an abstract class, so this is a heterogeneous collection. All intersectables are associated with materials. A material is a collection of material properties. Specific intersectable types can be implemented by deriving from the intersectable base class and giving the intersect function a real implementation. As for example, the sphere is also an intersectable. A sphere has two parameters, the center and the radius, and based on these two parameters, the intersect function can be implemented as the solution of a second-order equation.